You've got a bunch of capacitors here, but what do the numbers written on the sides of them mean? So there's 4,700 microfarads written here. What does that represent? Okay, so that is actually a unit for capacitance. So a capacitance of 4,700 microfarad means that on this capacitor, you'll be able to store 4,700 microcoulombs of charge per volt applied across it. Now, of course, if you apply more voltage across it, then you can store more charge. So for example, let's say I applied 5 volts instead of 1 volt. Then I would just take the capacitance and multiply it by 5 volts, and that would give me the charge stored, so 23,500 microcoulombs. So capacitance, the quantity, has a definition, and the definition of capacitance is charge stored per unit voltage applied across the capacitor, and is measured in farads. The symbol for capacitance is C. So it's easy to mistake that with the unit for charge. So here, and especially in this equation here, where C here is a capacitance, and that's measured in farads. So keep that in mind. Charge Q, which has units of coulombs, so capital C there. So it's easy to mix those up, so we need to be careful. And then voltage or potential difference in which has units of volts. Okay, and I prefer memorizing this equation as Q equals CV. The example question, the diagram shows a capacitor. An engineer wants to store 10 millicoulombs of charge on a capacitor and determine if the capacitor in the diagram is suitable. So we want to store 10 millicoulombs, but we've got some properties of capacitor that's written on the capacitor itself in the diagram here. It's got a capacitance of 22 microfarads, and that 400 volts, that is the maximum voltage I can apply across it before the dielectric starts possibly breaks. So we shouldn't go above 400 volts. Okay, so let's figure out the maximum charge you can store on it, and if that's bigger than 10 millicoulombs. Okay, so Q equals CV. So C, the capacitance in microfarads, I'm going to turn that into farads by times 10 to the power minus 6, and then times that by 400 volts to get a maximum charge I can store of 8.8 times 10 to the minus 3, which is 8.8 millicoulombs. So that means we don't have this capacitor isn't suitable enough. It won't be able to store enough charge. If we do try to apply more than 400 volts, it could break. So this is not a suitable capacitor. We need to give a conclusion like so. Example 2. The voltage across a 360 nanofarad capacitor is increased from 0 volts to 16 volts. Complete the graph. Okay, so this is Q against V. Okay, charge against voltage. So it's plotting this equation basically. Now in this equation, capacitance is a constant because we're looking at a particular capacitor in this question. So Q is directly proportional to V. So we should get a straight line that goes to the origin when it's directly proportional. So I'm going to put a cross at the origin because I know it's going to go through there. Then I'm going to use the equation again with this, let's use 16 as an example data point. So if I put in 16 and the capacitance, which is 360 nano farads, so I'm turning that into normal farads, and times that by 16, the voltage, and then get a charge that I can store of 5.576 times 10 to the power minus 6 coulombs. And the unit there, so if I find out the graph, that's over here, and I can join that using a straight line like so.